Everyone, welcome to the final session of the day. We have Yang Lee from MIT talking to us about metric SYZ conjecture. Over to you.
Thanks for the introduction. It's my great pleasure to speak at this wonderful conference. So today I'm going to talk about the metric aspect of the so-called Strominger-Yau-Zaslow conjecture. It's not XYZ. Strominger-Yau-Zaslow. Okay, so let me just begin with a quick reminder. I hope people here know about what Calabi-Yau manifold means. So this means a compact Kähler manifold with a nowhere vanishing holomorphic volume form, satisfying this partial differential equation known as the complex Monge-Ampère equation. So here the underlying data is you have x, which in typical applications come from just some equations cutting out some hypersurfaces or something like that in some ambient projective space. And you have this nowhere vanishing holomorphic volume form. So for instance, on Cn, a typical example of a holomorphic volume form is dz1 wedge dz2 onto dzn. So omega is the so-called Kähler form. It's a type 1,1 form compatible with the complex structure. And this data determines a Riemannian metric. And the main point is that if this equation is satisfied, then the Ricci curvature of that Riemannian metric is going to be 0. So that means the vacuum Einstein equation is solved. Notice that by definition, so here this holomorphic volume form, you wedge it with its complex conjugate. So basically you get a volume form out of this construction, and it's determined purely algebrogeometrically. Now here you have the Kähler structure, which encodes the metric. And this equation is basically saying that the volume form of your Kähler metric is prescribed to be this. So in particular, there's a canonical measure on the manifold coming from the volume measure. So the simplest examples that you can write down is just the Euclidean metric. So here the omega looks like this, capital omega is like this, and measure is just a big measure. And the simplest compact example, and essentially the only compact example which can be written down completely explicitly, is just a complex tori, Cn over lambda. Lambda is a lattice. Just for general interest, there is a non-Euclidean complete circle invariant Calabi-Yau metric on C2 called the Taub-Nut metric. And this example tells you that in general this is not that easy to classify. So even on C2 there are examples which are not Euclidean. And the typical compact examples come from algebraic geometry. So for instance, you can have a degree n+2 smooth complex hypersurface in Cp n+1. And the zero locus would give you an example of a Calabi-Yau. So maybe the easiest one that everybody learns in the first class on Riemann surface is inside Cp2, if you give me a degree 3 polynomial and take its zero locus, that would be a cubic curve, which is an elliptic curve. Now, the big theorem of the subject is, of course, Yau's famous theorem, which tells you if you have a given Kähler class on a complex manifold with this nowhere vanishing holomorphic volume form, then there's a unique Calabi-Yau metric within that Kähler class. Now, the second main player of this talk is the so-called special Lagrangians, defined by this condition. So this is a real n-dimensional manifold inside a complex n-dimensional ambient manifold. So complex n-dimension means real 2 n-dimensions. So these are half-dimensional submanifolds. The first condition is that the symplectic form or Kähler form omega restricts to 0 on L. So this condition is known as Lagrangian. That's basically the main object of studying symplectic geometry. So there's something in symplectic geometry called Weinstein's creed, which says that every question about symplectic geometry is a question about Lagrangians. Now, the second condition is that the imaginary part of the holomorphic volume form restricts to 0 on L. So notice this is a degree n form. L is a dimension n manifold. So this is top degree on L. Now, one reason people care about this is that these are minimal submanifolds inside the ambient Calabi-Yau manifolds. And in fact, it's even stronger. These are absolute volume minimizers within the homology class. And this is in fact a one-line argument. So there's a basic linear algebraic fact that if you, so this is just a pointwise fact, that if you take the real part of the holomorphic volume form and you compare this with the volume element on the submanifold, it's known that the real part of omega is always bounded by the volume element. So if you integrate this fact, you know that for any submanifold in the same homology class, you get a topological lower bound on the volume of the submanifold by integrating the left-hand side. And notice that omega is a closed form, it's a closed n form. So in particular, this is a purely topological quantity. And the main point is that this inequality is saturated if and only if you are a special Lagrangian. So in particular, if you can find a special Lagrangian in your given homology class, then it has to be the volume minimizer because you saturate the topological lower bound. The physicists call this BPS states. The simplest example of a special Lagrangian is you start with Cn with the Euclidean metric, and you take the standard copy of Rn inside Cn. That's a special Lagrangian. The simplest compact example is you just quotient out the above by a lattice, so you get a torus inside C star to the n. Now, in general, special Lagrangians are high codimensional minimal surfaces, real n dimension inside complex n dimension, so half-dimensional, and they often behave quite differently from holomorphic subvarieties, which are maybe the other most important class of high codimensional minimal surfaces. So in minimal surface theory, what happens is that people generally concentrate on what happens in codimension 1. And the high codimension examples, the general results are not that strong in comparison. And the construction techniques of special Lagrangians up to this stage is quite limited. So the SYZ conjecture is about the existence question of special Lagrangians in certain contexts. Okay, so here is the SYZ Strominger-Yau-Zaslow conjecture in a vague form. So the original paper is written in a physics type style, which means that to make rigorous sense of it, you need to make some interpretation. So the vague form of the conjecture is that for a suitable class of Calabi-Yau manifolds, in a certain limit called large complex structure limit, so later I will give you some example of what this can look like, you want to find a special Lagrangian torus vibration. So this means, okay, very sketchily, it means there's a vibration map from X to some base where the fibers, the generic fibers, are tori. Okay, so this is what you want to find. Maybe a picture of this. So I'm drawing the elliptic curve picture. Some kind of picture like this. And what you realize very quickly is that you have to allow for singular fibers, etc. Now, let me say a few things about what large complex structure limit looks like. So Calabi-Yau manifolds can degenerate by essentially two ways. One is to change the complex structure. The other is to change the Kähler class. Now, today we are going to focus on changing the complex structure. And what does this mean concretely? It means, well, Calabi-Yau manifolds are defined by some polynomial equations which cut out some hypersurfaces or some subvarieties inside a projective ambient space. And if you change the coefficients of those polynomials, then you get a family of Calabi-Yau manifolds. And you want to look at what happens to the metric as you change the coefficients to some limiting situations. An example of a large complex structure limit is the Fermat family. So the Fermat family is this explicit thing. Okay, the name Fermat family is actually my kind of propaganda. I thought people would recognize what this polynomial is. So what happens is that when s goes to infinity, well, this term, formally speaking, goes to 0. So algebra geometrically, if you just take the limit, you will get z0, z1, etc. The product is equal to 0. Now, what does that look like? It looks like a union of projective subspaces. So take the easiest example, the ambient space is CP2. Now you have a family of cubic curves, and in the limit you get z0, z1, z2 is equal to 0. That's a union of 3 copies of CP1s. Now, if you think about it, it doesn't really look like the metric limit. So then this is the point I want to elaborate a little bit. What does the Calabi-Yau metric on the elliptic curve looks like? It's the flat Euclidean metric on the elliptic curve. So the metric picture of an elliptic curve looks like this. I'm drawing a fundamental domain. Now, as you approach the limit, what happens is that you have a family of elliptic curves kind of with one side staying almost constant. There's another circle direction which shrinks down. So this is a general phenomenon, in fact. And in the limit, the metric limit is S1. It's a circle. Now, one thing to emphasize about the circle is that it's not quite a complex manifold. So as you look for the limits of these Calabi-Yau manifolds, the limit might not be algebraic. And that is quite a general phenomena in this kind of problems. So large complex structure is a particularly severe way of complex structure degeneration, so that the limit doesn't even look like a complex manifold. Now, how do you reconcile this algebraic limit, which is 3 copies of CP1, with this circle? If you kind of just look at the 3 intersection points, try to smooth them out a little bit, you will get this picture. Okay. Now, this you can probably recognize as a 2-dimensional torus. So what geometrically happens is that you have these small circle directions, and you have a longer circle direction. And metrically speaking, this collapses to S1. Now, the motivations for the Strominger-Yau-Zaslow conjecture for differential geometers, it's because we like to understand the Einstein manifolds and minimal sum manifolds. So we want to understand what happens to the kind of Calabi-Yau metrics, which are particular instances of solutions to the Einstein equation in certain limits. And we also like to find minimal sum manifolds, of which special Lagrangians are particularly important classes. Now, for complex geometers, we like to ask what kind of limits you can extract out of degenerating families of Calabi-Yau manifolds. So, in fact, this whole story is closely related to something called non-Archimedean geometry, which regretfully I will probably not have too much time for. There's another historical reason for the SYZ conjecture, which is that those people are trying to explain mirror symmetry. And the rough goal of mirror symmetry is to construct dual pairs of Calabi-Yau manifolds, and the complex geometry of one side of the Calabi-Yau is reflected by the symplectic geometry of the other dual Calabi-Yau, and vice versa. So that's the rough spirit of mirror symmetry. And the SYZ kind of heuristic for how this should work is that you should have SYZ fibrations, meaning those special Lagrangian fibrations on both sides, and they live over, roughly speaking, the same base. And what happens is that you replace the torus fibers on one side with the dual torus on the other side. So mirror symmetry from that perspective is just trying to do some kind of fiber-wise Fourier transform. you replace the torus with the dual torus and replace the data in a sort of Fourier dual fashion. Now, of course, this is somewhat of a lie for, a huge story. People spend their lives, trying to understand this, and this is too much of a cartoon for this. So the simplest case of the SYZ conjecture is just for elliptic curves, and as you see, it's understandable, but the metric limit is already not a complex manifold. What happens for abelian varieties is very similar to this case. Now, for all the other cases, there's no easy way to understand the Calabi-Yau metric. So when you move up the dimension to complex dimension 2, the only complex Calabi-Yau manifolds are either abelian varieties, which we already understand, or K3 surfaces. And in the K3 case, you already see some relatively serious stuff. So the prototypical work is the construction done by Gross and Wilson about 20 years ago. So what they studied is a K3 surface with elliptic fibrations. Now here is one thing to point out about what's special about complex dimension 2. So complex dimension 2 is the tangent space is modeled on C2. Now C2 is the same thing as the quaternions. And the quaternion has the special property that it's a complex vector space with respect to not just one complex structure. You have this IJK giving you 3 different complex structures. Right? In fact, you have a whole S2 worth of complex structures. And there's a trick in this special dimension called hyperkähler rotation, which is that a special Lagrangian fibration, a special Lagrangian with respect to one set of complex structure, Kähler structure, it can be interpreted as a holomorphic subvariety with respect to a different choice of complex structure. So this is a special feature about quaternions, which doesn't work in general. Now, having said that, what Gross and Wilson did was to consider holomorphic fibrations where the fibers are elliptic curves. These are known as elliptic fibrations. So what happens is that, well, maybe I should draw a picture or something. As you vary the Kähler class so that the fiber volume tends to 0, namely that this picture gets very, very squashed. So this is like size 01. This is like very small fibers. And there has to be some singular fibers. I'm trying to draw a nodal elliptic curve. Then what happens is that globally speaking, you collapse down to a smaller dimensional manifold. So here the base is CP1 or the same thing as S2. Now, as you try to understand what happens, in a smaller scale, well, there's a dichotomy about what happens in the generic region versus what happens in the general region, in the special region. So what happens in the generic region, generic meaning what happens on most of the measure, there's a canonical volume measure in this case. In the generic region, the metric is up to exponentially small error given by a semi-flat metric. And semi-flat means torus symmetric. So generic region in this picture means this region. You are trying to stay away from those singular fibers. And what happens is that the metric is almost torus symmetric. And the restriction of the semi-flat metric to the fibers would be Euclidean metrics by the symmetry. That's why they are called semi-flat. And the singular regions are the neighborhood of 24 nodal elliptic curves. 24 comes from the fact that K3 surface has Euler characteristic 24. Each singular fiber contributes 1. And there, the model metric is the so-called Ogre-Vafa metric. So that describes this region. And inside the Ogre-Vafa metric, there's an even smaller region called the Tavnat metric. This is Ogre-Vafa. one should say that those Ugurivarfa and top knot regions are actually super small as you approach the degeneration limit. Yes. Yes, but it's defined by a kind of infinite series. So it's defined using a Gibbons-Hawking construction of an explicit potential function, which it's obtained by a gluing construction. So it's explicit up to exponentially small correction terms. So here is the picture that I have drawn there. So you have these semi-flat regions. This is the most curved region described by the Ugurivarfa metric. And inside the Ugurivarfa, there's a smaller region modeled on the so-called Taub-Knot metric, which is a complete Calabi-Yau metric on C2. And this contains almost the entire L2 curvature. For complex dimension bigger or equal to 3, the metric version of the SYZ conjecture is quite hard. So what people generally did previously was to kind of try to avoid the understanding the metric, but instead focus on the mirror symmetry aspects. So there were huge progress in symplectic geometry and algebraic geometry trying to develop the enumerative theory and the Floer theory aspects of these things, kind of starting from Lagrangians, but not quite special Lagrangians. So if you just want Lagrangians, it's mostly a topological question. If you want special Lagrangians, you really have to understand the metric. And one reason the SYZ was considered quite difficult is because special Lagrangian fibrations are typically very different from holomorphic fibrations. So for instance, a holomorphic fibration, the underlying map is a smooth map, but that's usually not true for a special Lagrangian fibration. So let me give you a summary of what's known and then say a few things about what's kind of expected or conjectural. So the original SYZ conjecture involves two aspects. So the generic region and the special region where the curvature is very big. So the first result in general dimensions is for this Fermat family, which is quite explicit. So what's known is that the special Lagrangian fibration exists in the generic region when S is very large. So more precisely, what this means is that when S is very large, you can find a large open subset on which you can find a special Lagrangian fibration. And the probability measure, meaning the volume measure divided by the total volume of this open subset tends to 100% as this parameter goes to infinity. So in the limit, it covers 100% of the manifold. But for each particular finite value of S, you cover something like 99.9%. So the special Lagrangian fibration coming from this construction does not cover the entire Calabi-Yau manifold. It only covers most of the manifold. So there's a somewhat general result kind of based on a conjectural statement in non-Archimedean geometry, which would be able to imply the existence of special Lagrangians, at least in generic regions, in fairly general contexts, but that thing is not fully proved. The Fermat hypersurface example was recently revisited by Leonard Pili-Schneider and independently by Jakob Hutgian, etc. So those people improved the previous results a little bit. And more recently, the conjecture in Archimedean geometry is verified for a quite large class of Calabi-Yau hypersurfaces inside toric Fano manifolds. And what's involved in this is trying to solve a variational problem, which is basically about trying to get a real Montchampé equation, essentially. So this is what's known about the generic region. which has a very different flavor compared to what's known in the non-generic region. So in the non-generic region, there are some results in the direction of construction. So it's mostly about trying to generalize what happens in those complex two-dimensional examples. So the upshot is that in complex dimension 3, you can produce the analogs of the Oguri-Vafa and the top-knot metric on some local models known as positive vertex and negative vertex. Now, it's probably worth taking a while explaining where this terminology comes from. So what people expect about Calabi-Yau threefold is that, okay, so the SYZ fibration very optimistically should exist over S3, and inside S3, there should be some kind of trivalent graph, which morally speaking, you should imagine as discriminant locus. So that's not a precise statement. So what people expect nowadays is that you know, the singular fibers live over a small thickening of this trivalent graph. So away from this region, the fibers are kind of smooth. So this would be a torus. Now, when you study the local behavior near the edge of this trivalent graph, the transverse behavior should be modeled on what you already saw in complex dimension 2. Now, this leaves open the question of what happens around the vertices. And generically, people believe there are two types of vertices called positive and negative vertices with explicit descriptions of local complex structure. And these two things have Euler characteristic plus or minus 1. And that's why they are positive and negative vertices. So for the generic region, basically we have, so okay, I'm going to give you a review about what sort of things get involved in constructing, improving such theorems. The generic region has a completely different style compared to the non-generic regions. The generic region results, well, it involves some complex geometry, some basic differential geometry, such as dimensional reduction and semi-flat metrics. It involves Savin's small perturbation result on elliptic PDEs, some regularity theory of Riemann-Champais equation. Well, the main focus for me is really complex fluid potential theory, adapted to the degenerate setting. And for more general results, one needs some non-Archimedean fluid potential theory. So for the results in the high curvature regions, we currently only have constructions of the model matrix, and those results depend on Gibbons-Hawking type ansatz. And maybe the core part of the technology is the Jian-Yao-Hein strategy to find Calabi-Yau metrics in compact, non-compact complete settings. And the main construction is done by gluing type constructions using some ideas of Gabor-Zakahidi. And unfortunately, the construction involves quite complicated series and integrals, like things which look a bit like Weierstrass functions. So the old folks would like it. So what's believed is basically what I explained there. So that's the most optimistic hope, is that for Calabi-Yau threefolds, strict Calabi-Yau threefolds, you get this S3 as the base of the SYZ vibration, and you get this discriminant locus, which is thickening of the trivalent graph, and you have these local models, and modeled on those kind of local constructions. I should say that it's still kind of debatable whether or not there is actually a global special Lagrangian vibration. The theorems that people currently can prove is, in certain cases, you can prove there is a special Lagrangian vibration on most part of the manifold, but we currently don't have general results on, you know, global existence of special Lagrangian vibration, and it might not even be true. lots of things which are not understood. Now, the rest of today, I plan to give you some kind of sketch about what happens in the Fermat family case, which is the first case being understood in general dimensions. So the Fermat case is just this explicit thing. This is how you remember it. Okay. So the statement is that the special Lagrangian fibration exists on 99.9% of the measure of the manifold when S is very big. For each S, you don't get 100% big because there are high curvature regions which are not detected by this proof technique. So the generic region and non-generic region really behave very, very differently. So the generic region, the metric is almost symmetric. So the Lagrangian is what you might expect. It's a small perturbation of the almost flat torus, while what happens in the non-generic region is not very well understood. Okay, so the relatively easy part is complex geometry, and skipping maybe all the details, what you need to know is that you can write down local charts on which cover almost the entire manifold, but not every part of the manifold. And the local model is just C star to the n. So this is a feature of the large complex structure limit that you can find those charts which essentially give you C star to the n charts. Okay, let me skip this. So now there's something called the semi-flat metric, which just means torus symmetric Calabi-Yau metrics. And these things can be understood relatively easily. So you have, just imagine you are working on C star to the n. C star to the n has a map to R to the n by taking logarithm of each component. Now, suppose your Kähler potential is constant on the fibers, right? It's basically a dimensional reduction. So it factors through the logarithm map. Then this is a Kähler potential upstairs if and only if U is a convex function downstairs. And the Calabi-Yau condition is equivalent to this function downstairs, convex function satisfying so-called Riemann-Jampé equation, which means determinant of Hessian is constant. So these things are called semi-flat metrics because they are by definition torus symmetric, and a torus symmetric metric restricted to the torus is torus symmetric and hence Euclidean, hence flat. So, in fact, what one really wants to prove is that the true Calabi-Yau metric is very close to a semi-flat metric. And a semi-flat metric, when I put in all these normalization things that you don't want to see, looks basically like this, where this is the Hessian of a convex function, solving this Riemann-Jampé equation. Now, the good feature about semi-flat metrics is that the logarithm map going from C star to the n to Rn, the fibers of this map, so if your metric is actually semi-flat, then those fibers are just special Lagrangians. So if you can show on these local charts that the true Calabi-Yau metric is C infinity approximated by the semi-flat metric, then just by a small perturbation of the logarithm map, you would be able to produce the desired special Lagrangian fibration. So this is relatively standard deformation theory, which really means implicit function theorem. So the key thing to prove really is that the Calabi-Yau metric is close to being torus symmetric in a very strong sense. Now, now C infinity convergence is a very strong statement. So an important step in the proof is to reduce C infinity statement to C0 statement. So the C0 statement is that the true Calabi-Yau metric, once you write down the Calabi-Yau Kähler potential, that Kähler potential is close to a solution of the Riemann-Jampé equation, a priori not in C infinity, but just in C0 sense. This is like a convergence statement. Now, here the regularity theory of Riemann-Champais equation comes to save some work by saying that if you throw away a set with negligible measure, you can pretend the solution of Riemann-Champais equation is automatically smooth. Now, the main theorem that we use to reduce from C infinity estimate to C0 estimate is a rather difficult result of Ovidiu-Sabin, which people call the small perturbation theorem. And the flavor of this theorem is that for a large class of fully nonlinear second-order equations, including complex Monge-Champais equation relevant for the Calabi-Yau matrix, if you have a smooth solution and another solution you want to understand, which you only know is C0 close to the given solution, then you can in fact bootstrap from C0 to C infinity. So this is called small perturbation theorem because it turns out that the two solutions are C infinity small perturbations of each other. But it's actually quite a difficult result because for people who know about PDEs, you know that usually you need C2 estimates to begin to bootstrap. But this theorem is a little bit exceptional. It says that the condition is only C0. So the point of this theorem in our context is that we can reduce C infinity to C0. And C0 things are the realm of fluid potential theory. The word fluid potential means scalar potentials. Okay, so well, the word fluid potential comes from is really the generalization of subharmonic functions. So what you learn in complex analysis is subharmonic functions. Fluid potential theory is the study of subharmonic functions, the analog of that in several variable complex analysis situations. Okay, so what you need to achieve is the C0 convergence statement, and that involves doing two things. One is to produce a solution of the Riemann-Champais equation. The other is to prove their true Calabi-Yau metric potential is close to that Riemann-Champais solution. So I will try to give you a little bit of flavor. So the intuition is that if you're working on very long cylindrical regions inside C star to the n, then Kähler potentials look very similar to convex functions. So how do you compare a general Kähler potential on C star to the n to a convex function? Well, one way to think about it is that, well, a Kähler potential is basically a fluid subharmonic function, and you can average in the Tn direction to produce a convex function. That amounts to taking the fiberwise average, or if you want, you can think of this as a zeroth Fourier mode. So what happens is that it's almost automatically true that this Kähler potential is close to the convex function in a strong integral sense. And then some, okay, so you need to use some relatively heavy machinery in fluid potential theory to say that these two things are in fact close in some C0 sense. So let me just show you a little bit of inequality so that this talk has some estimates in it. So the Calabi-Yau potential is close to that convex function roughly by these two estimates. So there's an upper bound. So when S is large, this is a very small quantity. Now here is a slightly more tricky thing. So it's a lower bound on this quantity. So notice that the exponent is proportional to the square root of S, which is a very large quantity. So what happens is that this quantity may be quite negative, but it can only be very negative on a very small measure. It's almost, okay, I'm almost done. So, so this is saying that up to very small measure, this thing is bounded from below. Now, what you need to do is to adapt Cologi's package of complex pluripotential theory to improve the above estimate so that you remove this very small subset and prove that the Calabi-Yau potential is very close to that convex function. Now, once you know that the Calabi-Yau potential is very close to the convex function, that shows that the Calabi-Yau potential is almost torus symmetric in a weak way. And then you still need to understand exactly where the Riemann-Champey equation comes from. Well, so the rough idea is that you already know that the Calabi-Yau potential is close to a convex function. And then convex functions automatically have some kind of Lipschitz bounds. So by some Arzelà-Ascoli type argument, you can try to extract some limit. And then you can use the equation on the Calabi-Yau potentials and try to take a limit in a somewhat clever way to prove that this limit in fact satisfies the Riemann-Champey equation. And essentially by construction, this convex function has this limit. So this limit is close to the convex function in C0 sense, which is in turn close to the Kähler potential of the Calabi-Yau metric in C0 sense. So what you get in the end is that the Kähler potential of the Calabi-Yau metric is C0 close to a solution of the Riemann-Champey equation. Now, the gist of this argument is that this is the C0 statement, and Savin's result allows you to bootstrap from C0 to C infinity. And then once you know that the metric is close to being semi-flat, it only takes some implicit function theorem argument to produce this special Lagrangian fibration. I guess I have run out of time, so thanks. Okay, so I guess I already finished for this talk anyway. So I slightly rushed towards the end, so if you want me to repeat something, I'm happy to.
Yeah. Do we have any questions for the speaker?
Yeah.
What about the model metric around the singular fibers?
Okay. So this question actually has. Okay. So are you asking about the two-dimensional higher?
Higher.
Okay. In higher dimensions, what we have is the construction of the model, but we don't know how to prove the model actually arises in compact examples. Does that make sense?
Okay.
So, and the construction of the model first involves a Gibbons-Hawking pipe ansatz. Okay. And, okay, so maybe I can tell you what the two-dimensional thing looks like if you want, if that's what you want to ask.
So thank you. So the second question, so do we have some results in higher dimension when it has an elliptic fibration, so that we can use lower dimensional results?
Okay, so what has been done, in fact, a long time before this work, is people can study the hyperkähler case. So people have studied the case of abelian variety fibration case. So what people start with is a hyperkähler manifold with an abelian variety fibration where the fibers are so-called holomorphic Lagrangians. So this kind of stuff is very popular in algebraic geometry. So there's things like Matsushita theorem, etc. So within that setting, Valentino Tossati and his collaborators developed some kind of structural theorems about what happens in the generic region. But these types of techniques depend very heavily on the fact that you can turn the problem into a holomorphic vibration. And for holomorphic vibrations, you have many extra tools. And what you can sort of prove is that in the generic region, you have nice convergence results. In the fibers, you have, the fiber metrics converge to almost semi-flat metrics, etc. But these methods don't generalize to general dimensions. They only work for hyperkähler.
Okay, thank you.
Any more questions for the speaker? If not, let's thank the speaker again.